Hello everyone, this is Tong from Alibaba. Here I'm going to introduce this paper in ATC. Since the first author was unable to obtain a visa, so I'm stepping in to present this paper on their behalf. This work is done in cooperation with Shanghai Jiao University. Here is the outline of my presentation today. First, I will introduce the background and the motivation of this work. Cloud-native computing has become predominant in recent years. Application experienced a major shift from monolithic design to microservice-based architecture. It also brings more complicated dependencies between application and network. Meanwhile, cloud vendors adopt mixed deployment of lots of applications to improve fundamental resource utilization. In the practice of Alibaba Cloud, operators co-locate I/O-intensive big data jobs and CPU-intensive online services. Such a mixed deployment causes more resource-constrained cloud-native environment. The emerging cloud-native computing bring challenges in detecting and diagnosing application and network anomalies. Next, we present three practical issues happening in the long-term operation of Alibaba Cloud as the motivation of this paper. First, most widely deployed network probing system focus on virtual and physical network layers. They may achieve a full mesh probing at the host level, however, cannot access actual impacts on each microservice. For example, as shown in the right figure, ping system probes each node and link at the same time. However, it cannot capture actual weights of critical microservice. For example, the in-memory database proxy and the load balancing. As a result, probing results can be easily covered by noises of prevalent network jitters in production environment. Second, with a microservice-based architecture, the root cause of application anomalies is usually attributed to dependent microservice or shared infrastructure. Currently, operation teams and specific monitoring tools focus on their own problem domains, software, operating system, and networks. The clouds lack a unified diagnostic mechanism to correlate layers, components, and root anomalies to attribution teams. Last but not least, the number of microservice instances or container IPs reach million level in a single cloud regions. As an always-on service, the monitoring system should be carefully optimized for low computational and storage overheads, the lower the long-term capital and operating expenses. Okay, so on this basis, we summarize the problem definition of cloud-native diagnosis system. Our two goals are to ensure SLA of customers and QS of applications. We define application network anomalies at three levels according to their severity. Firstly, application shows performance jitters when the expected SLAs of customers are satisfied. Secondly, application experience several performance declines in throughput, latency, job completion time, and the SLA of customers are violated. Thirdly, services are unavailable and anomalies upgrade to failures. In a cloud-native diagnosis system, anomaly collecting in the preliminary, it also collects and performs filtering on massive metrics. After collecting Anomaly detecting extract anomalies that has several impacts on SLA and QoS in real time. In practical usage, anomaly routing to target application or network anomalies is indispensable for faster future localization and recovery. Next, we present Unicode challenges in resolving the above problems and the design of application network diagnosing system in Alibaba. So it takes TCP. This system takes TCP retransmission as basic metrics. It builds unified anomaly monitoring and diagnosing capability covering the whole cloud. The key insight is that retransmissions are effective signs of anomalies inherently exist in inbound traffic and correlate applications to fundamental platforms and infrastructure end-to-end. In practice, and further encounters 3 deployment challenges. Firstly, production clouds unexpectedly show massive retransmissions. For example, the number of retransmissions of single microservice instance reaches 10 to 1 million per second and show a long tail nature. Secondly, the root transmissions are too noisy to reflect anomalies that cause SLA violation. This makes the deployment in public clouds. Applications show distinct patterns of retransmissions. For example, the latency-sensitive services cannot tolerate timeouts and have few retransmissions, but the background tasks has many retransmissions in daily operations, so long as tasks completion on time. Thirdly, anomaly routing and locating are non-trivial with at least 5 attribution teams and 5 traffic scenarios involved. Next, we introduce AND system to tackle these challenges. In the left figure, AND covers anomalies below application layer. From a bottom-up perspective, including physical and virtual network, physical NIC, vSwitch, virtualized net device, kernel stack, and even abnormal application behaviors. So the right figure shows the overall architecture of AND incorporating anomaly collecting, detecting, and diagnostic. The process from anomaly collecting to routing takes less than 1 minute in the first step, and monitors retransmissions at end hosts via a dedicated tool, namely NBPF. It then performs real-time anomaly detecting on time series with transmission counters. Finally, the abnormal IPs are aggregated by application and network attributes and exported to the diagnostic process. NBPF designs eBPF-based kernel filters to extract prominent anomalies that impact application performances. For example, the fields of connection establishment and retransmission timeouts. In the initial deployment, and collects all retransmissions without filtering. We observe that applications show massive retransmissions because the end host and network jitter easily cause massive TLP or faster retransmissions. NBPF thus filters retransmissions by taps and connections in the collecting phase. NBPF also devices user space filters to record accurate retransmission counters and sample retransmission details. It monitors retransmissions from each microservice and container instance sharing one kernel. and NBPF distinguishes multiple traffic directions and scenarios via configurable filters on destination IPs. Then, the CPU and memory usage of NBPF is carefully optimized. The NBPF agents read retransmission events from kernel space via zero-copy ring buffer. The CPU quota is limited to 5% of one core, and the memory quota is limited to 30 megabytes via C group. Overall, NBPF effectively filters out more than 90% of retransmissions and achieves the low overhead in heavy stress tests with million connections, and adopts multi-level time series clustering to distinguish distinct retransmission patterns. The time series are first clustered according to the frequency of retransmissions. Specifically, time series are divided into 4 levels from low to high frequency to reflect that noise level. On this basis, and further classify the time series into stable tape and unstable tape. Unstable tape may include seasonal trend, mean shift, and hybrid tapes. The bottom figure presents the distribution of retransmission patterns in cloud intranet scenario. Most time series are stable or seasonal, as the network environment of the intranet is relatively stable. Even so, a large portion of time series will still show noisy patterns and can not be filtered simply using the thresholders. According to the clustering results and the design's lightweight feature engineering and extracts normalized features for anomaly detection. The computer-intensive clustering and the model training are conducted in the offline phase. The feature extraction and anomaly detection are executed in real time finally and achieve the minute-level detection for millions of time series. And uses a hierarchy diagnostic mechanism to narrow the scope of problems step by step first, and distinguish the anomalies between intranet and internal traffic in the collecting phase. After that, and routes anomalies among network, non-network, and special scenarios like SLB, NAT, and internet. The routing model uses the distribution of retransmission as the feature to classify network and non-network anomalies to depict the distribution of retransmissions. The destination and the source IPs in retransmission details are aggregated by application and network attributions, and adopt a classification model based on the gradient boost decision tree. It collects labeled anomalies and failures in practical operation as training sets. Next, we present the deployment and evaluation results of AND. As shown in the right figure, the CPU overhead of NBPF keep around or below 1% of single core. NBPF only collects retransmission events with dedicated optimization like filtering, sampling, zero copy collecting, and so on. The outdated netlink interface collects the TCP information from the kernel. The BCC tool is responsible for monitoring TCP connections using eBPF. The burst loads easily cause a full occupation of a single CPU core for netlink, and the peak CPU utilization easily exceeds 10% for BCC. In the right figure, right, we show the efforts of the detection phase. The detection phase eliminates the noise of time series by lightweight prediction. The features are also penalized and scaled via coefficients in cyclic windows and variance in short time windows. We conduct a 1-month evaluation considering network anomalies. We define 10 orders of severity according to the scope of anomalies. From the L0 to L9, the number of abnormal IPs exists to 0.1% to 1% of the total number of monitored microservice and IPs. Recall is defined as the percentage of network anomalies detected by and among all network anomalies. Accuracy is defined as the percentage of true network anomalies among network anomalies detected by and. So the false positives are mainly attributed to wrong conclusions. For example, large scale and host application anomalies may be wrongly attributed to network anomalies. The false negatives are due to the different design rationales of and the probing system and monitors in bound traffic of applications and reports anomalies only if application traffic is impacted differently. Probing systems are sensitive to network jitters. However, application traffic may not pass the problematic links. Overall, and achieves around 95% recall and accuracy at the highest severity. We conduct next we present experience and summarize the conclusion. As shown in the left figure, during SLB overloading, the pin system cannot tell the scope of anomalies by probing destination IPs and reports the number of affected source IPs. After checking the traffic of SLB nodes, we observe the SLB nodes are overloaded and thus drop many packets as shown in the right figure. Network teams often perform gateway alternations and upgrades. As shown in the left figure, the related IP segments will burst many retransmissions due to connection breaks and the recover to normal and helps detect unexpected gateway cluster failures quickly during alternations, as the right figure shows. The operators then execute rollback action and the applications recover to normal rapidly. Network and application anomalies show distinct distribution of the abnormal IPs and builds an anomaly routing model based on this observation. We believe and is a success attempt toward AI whoops and thus release the burden of operating teams. Here come to the conclusion. In this paper, we present application network diagnosis system and uses a single metric of TCP retransmissions to build the unified monitoring and the diagnosing capability. Cloud operators usually use two ways for faster future recovery of services and applications. First, operator contact application teams to migrate their virtual machine or container instance to redundant machines at the data center level. It relies on impact assessment from the application perspectives. Secondly, operators find the attribution team of the future, pinpoint the root causes and locations, and repair features on site, besides, and achieve very low overhead and good generalization. As future work, we explore internet measurement from perspective of cloud vendors. Besides, there still exists a large room for QoS improvement from the application perspective. So this is the presentation. Thank you.